Can I start? Okay, we are going to start. Welcome everybody. Good morning. So I'm Jesus Villalba. I'm going to teach today the tutorial of speaker recognition. So I'm going to start introducing the roadmap of today. So we will start with an introduction to what is speaker recognition, the terminology, and how to measure metrics in speaker recognition. Then we will see a little very brief introduction to how was speaker recognition before deep learning. And then most of the time we will spend in seeing how to do speaker recognition using neural networks. Basically, we will describe the different architectures, pooling mechanisms of functions. Then if we have time, we will talk a little bit about the backend and other topics, but probably we won't have time for the other topics. So let's start with the introduction about the task. So speech is a signal that encodes a very diverse range of information. So for example, if you want to know what a person said, you do speech recognition, right? You want to know the language in which a person is speaking, you do language recognition. So in this tutorial, we're interested about speaker recognition, which is identifying who is speaking. Something that is also related to speaker recognition that it will be tough in the second session is speaker diarization, which is saying who speaks when. So basically, it consists of taking an audio where you have multiple speakers and splitting this audio into homogeneous segments of single speaker, and then with deciding how many speakers you have and when each person starts and ends speaking. Then we have also emotion recognition, that is determining what is your emotional state. And you can have categorical emotion recognition where you detect if someone is happy or sad, or you can have regression style emotion recognition where you detect values of balance and arousal of the person. And finally, we can also have medical applications of speech. For example, pathology. You can detect several pathologies from speech. You can detect Parkinson, you can detect dementia, other types of pathologies using speech. So here in this tutorial, as I said, we are going to talk about voice biometrics, also called speaker recognition. Basically, speaker recognition is a biometric modality consisting of recognizing people from the characteristics of their voices. Why can we do that? It's because our speech is influenced by two factors. First, the anatomy of the individual, basically the shape and size of the voice production organs, like the vocal tract, larynx, and nasal cavity. It changes the resonant frequencies that of our speech, and that will allow us to differentiate one person from others. Also, there are behavioral patterns that we call the manner of speaking. So each person has, depending of factors like where have you lived, which is your language, your, let's say, social background, you will have different accent, you will have different rhythm, intonation style, pronunciation pattern. You will use different vocabulary depending of your educational level too. So that will help, that can be used also to discriminate one person from another. So there are many types of biometric modalities available. You have speech, fingerprint, DNA. But speech has certain advantages. Basically, one is that it's easy to use because speech is a natural way of communication, and also it's non-intrusive. That means that it can be well accepted by users. Because, for example, if you want to use the fingerprint, usually you have to put the fingerprint in some sensor that may be dirty and you don't want to touch. You know, with all the COVID thing, we have been more careful with what we touch, and we are more conscious of having some kind of sickness because we touch something that has some kind of virus or something, right? So what are the applications of speaker recognition? So we have several applications that you can use speaker recognition for. One of the most important is law enforcement and forensics. For example, imagine that the police knows that some kind of criminal organization is operating in some kind of area. So you can ask to a judge for a permission to listen all the conversations that happens in the base stations or the base stations of that area, the mobile, what people speaking with their mobile phones. And then you acquire those audios from the base stations, and then you apply speaker recognition to those audios. So then you can detect the criminals, right? And then you can send those audios to the police. Also, you can use it for when there are telephone threats and you have a recording, you can detect who is doing those threats. Also, if you have, for example, a person that usually commits fraud by telephone, for example, calling to some kind of service to contract that service using another person's name or something like that. So usually you can get some kind of, so those recordings those calls are recorded, and then you can put those criminals, when you detect them, you can put those criminals in a blacklist. So next time they try to commit fraud, automatically that recording goes to the speaker recognition system, and this person is compared with the blacklist, and then it can be detected that he cannot commit fraud anymore. Also, in forensics, so a voice sample which is taken in the crime scene is compared to the speech of the convict, and you can use it to say that is the person that was in the crime scene or not. Also, another common application is identity authentication and access control. For example, you want to access a high security facility. You could have, for example, a military base, an airport, government building. You could have some kind of identity card, but that could be stolen. So to get access to this restricted area, you could have the combination of the identity card plus some biometric modality, for example, speaker recognition. You can also use it to access computer network, websites, to reset your password. Also, it's very commonly used in telephone banking. So you want to do some operation in your bank account through telephone. Speaker recognition is a way that that the bank will use to authenticate you. So another application is meeting transcriptions. So this is more for speaker diarization. So you have some kind of, you have a meeting with your company with several people, and then you want to have some kind of, you want to record that meeting, and then you want to have some kind of summary of that, saying, for example, this person said this person said that. So you could use speaker diarization to segment the audio, and then once you have segmented the audio, you apply JSALT to the different speakers, and then you can know, you can have some kind of summary of the meeting, and then you could even take this information and send that information to a large language model to get some kind of more summarized version. Also, for audiovisual media indexing, you have, for example, broadcast TV, YouTube. Basically, these services produce a huge amount of data, and maybe you want to have some kind of way of finding searching people in this data. For example, I want to know all the speeches from Biden or from somebody. So you could use speaker recognition to add metadata to the videos and make this more easy. Also, for personalization, for example, you have a voice assistant like Alexa in your house, and you will have this device can have a speaker recognition, and then you say, for example, play my favorite music. You can know who you are, so then you can have a different playing list per user, and then without saying who you are, basically the speaker recognition will decide which is your playing list and will play that one. You can use it also to read user emails or for parental control. Any questions so far? No. Okay, so when we talk about the speaker recognition, we can talk about two different tasks. One is speaker classification or speaker identification. This is basically determining whether a test speaker matches a set of known speakers. So basically, you will have a series of people enroll in your system, and then when you have a test sample, you will say which one of these persons are the ones in the test sample. For example, here in the picture, we have both Alison and Peter, and when we use the system, we can have to choose one of those three. This is also called closed set identification. This is usually not what we do when the most applications about speaker recognition deal with speaker verification. So speaker verification is determined whether a test speaker matches a specific target speaker. So basically, in this case, we will have some you will enroll a person in your system, for example, Bob, and then we'll have a test sample, and we have to say if this person's Bob or not. So basically, we just compare the test sample with the sample of that Bob provided at enrollment time. And then that means that the test sample may come from Bob, or may come from any other person in the world. And we have to be able to discriminate Bob from any other speaker. So this is usually called as open set verification. And that is when you, with most companies that have some kind of speaker recognition product, this is what they provide, because it's what usually makes sense, because you don't know who is the person that you are going to have in the test sample. You cannot have your test sample limited to a subset of the closed set of the speaker. So in this tutorial, we are going to focus on speaker recognition with neural embeddings, since neural network embeddings are the state of the art for speaker verification. So a speaker embedding is some kind of vector, a fixed length vector that compresses all the information that you have in a variable length recording, retaining all the biometric information and discarding all other types of information, like what the person is saying or what is the person emotion. So when we compare the enrollment and test embedding, we can decide if those two come from same person or from different person. So in this tutorial, we are going to learn about the general speaker verification pipeline using embeddings. What are the neural architectures that we use? What are the train loss functions? And what are the backends that we use to compare two embeddings to say if they come from the same speaker or from different speakers? So the speaker verification pipeline, we have three phases. So in the first phase, what we call the training or development phase, we take a training database where we have several audios from a large number of the speakers, typically thousands of the speakers. And for each speaker, you want to have several audios per speaker. And hopefully, those audios should be taken in different sessions separated several days. So because if you take all the audios in the same session, there is very little, let's say, intra-speaker variability. And you want your system to be able to learn how the voice of the speaker changes when time passes, right? So you want to have audios for each speaker. You want to have audios that happens in different conditions, in different situations, different days, maybe different emotions, or the more variability, the better. So your model can learn to find what are the attributes that discriminate between speakers and remove all the attributes that don't help you to discriminate between speakers. So you will take this training database and you will extract some kind of acoustic feature. And then you will do statistical modeling. Mostly right now, this kind of statistical modeling basically is training a neural network, a speaker embedded neural network. And then you may have to train some kind of metric model that helps you to compare embeddings. And you may have also to train some kind of calibration model. So the calibration model will help you to transform the metric that compares the embeddings of two audios into some kind of measure that has probabilistic meaning. So then once you have your system trained, we have the enrollment phase. So for example, here we have Alice, and we are going to enroll Alice into the system. So for that, we again extract acoustic features for Alice, and then we calculate the speaker embedding using the speaker embedding model that we already trained in the training phase. And then we save this speaker embedding in a database of enrolled speakers. And then finally, we have the test phase. We have an audio that a person that says that, hello, I'm Alice. So we want to know if that's true or not. So again, we extract the acoustic features from this audio. We extract the speaker embedding, and then we compare both embeddings. And then this metric block will produce a number, and this number is high. That means that it's high probable that both audios come from the same person. And if the number is low, that means that both audios are probably not from the same person. And then we have this optional block, that is the calibration block, that will transform this number into something that has probabilistic meaning, like a log likelihood ratio or a posterior probability. So what is, for example, we can then ask what is the posterior probability that the unknown test come from Alice, right? And then once you have this posterior probability, at the end you always have to take a decision, yes or no. Yes. What?
Metric, something or is it fixed?
So the metric can be just cosine scoring, or it can be some kind of another model that you train on top of the embedding. So for example, it can be probabilistic linear discriminant analysis, it can be linear discriminant analysis, or it could be logistic regression or something.
What's sex difference? Well, say not the same. Or how is this training?
Oh, we will see it later. Yeah, this is just the general architecture. Okay, so yeah, so once you have your final likelihood ratio or posterior probability, you have to take a decision, and for that you have to put a threshold. And then you take the decision, accept Alice or don't accept Alice. So we can start seeing each one of the blocks. So the first block are the acoustic features, and the most common acoustic features are Mel filter spectral features, Mel filter spectral. So basically, what you do to calculate these features is you take your audio, and knowing that even audio, the speech is a signal that has a statistic that changes over time, you can assume that in short periods, there's a statistic more or less constant. For example, in short periods of 25 milliseconds. So what you do is you put you use a sliding window, right? And for each of those windows, you calculate the Fourier transform, and then you calculate the magnitude of the Fourier transform. So you get just the energy information in the different frequency bands, and then usually you put what we call a Mel filter band. So the Mel filter band has this shape of triangles that become larger and wider and wider when you increase the so for low frequencies, those triangles are narrower, and for large frequencies, those triangles are wider. So basically, what these do is basically you take these triangles and you multiply them by the magnitude of the Fourier transform, and then you take the sum. And what you do by that is just calculating the average power in the signal at different frequency bands. So the first triangle may calculate the power of the signal between 64 Hz and 80 Hz, and the last triangle may calculate the energy of the signal between 7 kHz and 8 kHz, more or less. Usually, so these triangles are designed in some way that mimic the human auditory system, where we have also less resolution in high frequencies and more resolution in low frequencies. And then you have a logarithm operation that compresses the dynamic range of this energy estimation, and then you get your vectors. So you do that for each window. So usually you have windows of 25 milliseconds with a shift of 10 milliseconds. So from this operation, basically what you get is a matrix of time times frequency, where each of these columns here are the Mel filter bands at a given time step. Okay, and you get a sequence of vectors, usually, or you get 100 vectors per second. Okay, any question about that? Okay, so once you have the acoustic features, you will calculate the speaker embeddings. Why do we calculate the speaker embeddings? So suppose that you have some enrollment audio where the Mel filter bands look like this, and some test audio where you have these other Mel filter bands. So if you want to compare these two matrices, it's going to be difficult, right? Because each of these matrices have different durations, and in each of these matrices, the person says different things. So you want to do some kind of minimum correlation, you will have to find common phonemes between those two matrices and compare how this person pronounces each one of these phonemes. So you want to do that comparison, you have, okay, what this person said, like, I'm inventing this, but this person said here, and his person says here. So you have to take this chunk and then this chunk and somehow compare it. So that is very complicated. So what we do is just to have some kind of method to transform this sequence of features into just a single vector per utterance. So you will take the audio, you calculate the features, so you get 100 vectors per second, and then you put this into a neural network that is trying to discriminate the speakers, and then you remove the last part of this network, and then you extract features from the middle here, where you have this sequence of features here, you get a sequence of features here, and then you got some kind of pooling mechanism here that averages this and gives just one vector, and here you just have one vector per audio. And then you can extract this vector, and this will be what we call the speaker embedding, so you get one vector per recording. And to train this model, you will have a large data set of speakers, as I said, and so you have a model that is able to generalize. Okay. So then you have, once you had your speaker embeddings, you will have what we call the metric or the backend. So you have some WE speaker embedding from enrollment utterance, and you have WT, the speaker embedding for the test utterance. You can just, so the most simple thing you can do is to do the cosine scoring with these two vectors, right? To get some kind of measure of these vectors are close or not. Another method will be PLD, and we'll see more in detail this at the end of this session. And then we have the calibration block, and the calibration block is also about how to choose the threshold. So basically you have your speaker verification system that produces a score, and then you have a threshold to decide if you accept or reject. So how do we choose the decision threshold? So if we have a high security application, we need to accept very few test samples. So we have to put a very high decision threshold. So for any kind of security application, we will have to use this, or for forensics. If we have a low security application, like meeting transcription, or for example, you are in your home and you are using Alexa. So those are situations where you have low risk. So you can use in those cases a low decision threshold. And then once you have your decisions, you have to calculate how good is your system or how bad is your system. So for that, what we are going to do is we are going to have a test data set where you will have what we call the target trials. Target trials are the trials where the enrollment and test are from same speaker, and then we have non-target trials or impostor trials where target enrollment and test come from different speakers. So you pass these audios through the speaker verification system, and you get the scores. And then you calculate what are you get the scores. You apply the threshold, and then you calculate how many errors you have of each type. So when you do that, you will get scores that look like more or less like Gaussian. So this will be the distribution for the target trials scores, and this will be the distribution for the imposter scores. And here you put the threshold. So basically all the scores that are target and are below the threshold will be false rejections. All the scores that are imposter and are above the threshold, they are false acceptance. Basically, the false acceptance ratio will be the area under this curve, and the false rejection ratio or miss ratio will be the gray area here under the target distribution blue line and below the threshold, right? So usually we are not going to just measure these metrics as a single threshold, but what we will do is to calculate these metrics for multiple thresholds. So we'll move the threshold and we'll calculate those false alarms and false rejections for different thresholds. And then we will get multiple false alarm, false rejection pairs. And then we can use those to plot what we call a detection error trade-off curve. Basically, is what measures the false alarm versus the false rejection rate. Okay, so you have so what you will do is you get your scores. Then you have for all possible thresholds, you calculate the pulse acceptance and false rejection pairs, and then you can plot this curve. And then the closer this curve is to the 0, the better is your system. Okay. One metric that is commonly used is the equal error rate. It's the point where the false rejection rate is equal to the false alarm rate. So basically, it's the point where the detection error trade-off crosses the y equal x line, right? So this is the most common metric that you will see in papers for speaker recognition. And then in these speaker recognition evaluations, the method that is used is what we call the detection cost function. So usually the reason, so in this evaluation, the reason not to use the equal error rate is because usually when you set up a system in real life, you are not going to put your threshold in the point where you get equal error rate, but you will put your threshold closer to 0. You will put your threshold in a point where you have low false alarms for security applications. You will choose a threshold for low false alarms and high false rejections. So equal error rate, which is over here, is not the best place for actually real application. So in that case, we use the detection cost function, and the detection cost function is a weighted average of missed rates and false alarms. And this beta is what determines what is the weighted average, and this beta is equal to the ratio of 1 minus the prior probability of having a target trial divided by the prior probability of having a target trial. So prior probability of having a target trial will be given in a way that will someone tell you, okay, from all the trials that I'm going to have, I expect that 10% of those will be through target trials, and 90% of those will be impostor trials. So you can calculate this detection cost function also for multiple thresholds, but depending on beta, there will be a point where you have a minimum detection cost function. So you can calculate what is the threshold that minimizes the cost function, and that's one of the metrics that we also use normally, is the minimum detection cost function. And then we have also, yeah.
Is it, but doing like sample by sample, or how do you decide like whether you hit or missed in a signal?
Yeah, you do it sample by sample.
But then it's dependent on the rate of sampling and this stuff.
No. You decide. You take a decision per audio.
Sorry?
You take a decision per audio, not per sample. You mean when you mean sample, you mean like?
Like no, the hertz, really the hertz of sampling of the audio. So if you have 16 kilohertz versus 8 kilohertz, you get a different number of samples to compare. So
no, but you take your audio and then you get one vector per the whole audio. You don't do comparisons sample by sample. I mean, when I say sample, I mean the whole audio, not the.
What I mean is, at ICASS 2017, I was approached by one of these guys from Diarization, and they are using these clustering approaches.
Yeah, so you do a speaker diarization, usually you will take a decision per second or per 3 seconds, depending.
Time scale rather than on sampling scale, let's say. And so this is not something that would be mainstream now. They were using purity and coverage for the evaluation instead of true positive, false negative, and so on.
Yeah, because that is a clustering problem. So you need to use other metrics.
Maybe I can later, because I'm not from the domain, and he just was really persuasive, and he had really good arguments. But I still, in literature, I'm not sure what is like the typical way to do it. So from your perspective, this is the way to go.
Yeah, this is the way to do for speaker recognition. For speaker diarization, you will use speaker priority, cluster priority, or diarization error rate.
Okay, so that might,
Yeah.
Okay, so that's
yeah. Okay. Any questions so far? No questions. Oh, the p-target is the prior probability of observing a target trial. That is, for example, if you have some application where you expect somehow that 10% of your trials will be target trials and 90% of your trials will be imposter trials. So you have to have some kind of estimation of how what you are going to get, right? Yes, it's a priori, something that you expect to have a priori. And based on what is your expectation a priori, you set your decision threshold to minimize this cost function. And then that's what we call the minimum cost function. Then we can have also the actual cost function. For example, you have some a priori beliefs, and then you set, you choose your threshold theta as a function of the prior beliefs. And then at test time, the reality is different. You won't get the minimum cost function, you will get what we call the actual cost function. Okay. Yeah.
So with one embedding vector per audio clip, how long is the clip? Is it like sometimes is it like a 5-minute recording or statistics? So we've got multiple clips that we classify and get
Yeah.
from, right?
Yeah.
So how many clips are those and how many they are?
So usually you will use thousands or millions of trials. So that depends also on how good your system is. The better your system, the more trials you need to get some metric that is statistically significant. Because suppose that you have, so basically how many trials you need depends on the number of errors you get when you evaluate the system. So for example, you have a system that is very good, and then you got just 10 errors. Having 10 errors, you can calculate the equal error rate with 10 errors, but that means that equal error rate that you are calculating is not very reliable. So you will have a very large, let's say, confidence interval. So you should also calculate confidence interval. For example, you will get that the equal error rate is 1%, but plus minus 2%. So when you have so if you have system that is very good, you will need millions of trials. So you get at least a few hundreds or a few thousand errors, right? So those clips depend on the application, can be from 10 seconds to 5 minutes. Yeah. So each time we are trying to make them shorter and shorter. So in early times, usually those clips were, you compare 5 seconds against 5 seconds, that would be in the 2000s. And now usually those clips are, usually you will use something between 10 seconds and 60 seconds for enrollment, and maybe 10 to 30 seconds for tests. And then you can also measure how good is your system for different enrollment and test durations. Yeah.
Now I have like n embeddings here and embeddings here. So how do I make those up? Do I do like all the possible pairs?
Okay, so there are several methods to do that. So you have, for example, several enrollment audios, right? So you can just take the average of you have several enrollment audios, and one way is you concatenate those and you get one embedding. Another method is you calculate one embedding per audio and you average it. And then when you use a probabilistic model like PLDA, you can have what we call the by the book evaluation, where that kind of model can handle multiple enrollment and test embeddings. So that kind of model, you can say, okay, compare this n enrollment embeddings versus this m test embeddings. But even it's theoretically the best way, is the theoretically correct way to do it. Usually what it works best is just to do the average. You do the average of all the enrollment audios, the embeddings on the enrollment audios, and you do the average of all the embeddings of the test audios, and then you just compare it to. And that is what is the best result. Yeah.
are any other ways you can combine these embeddings other than the average? So could you tell us a bit more about what has been tried and like why is it the average the one that works best? Like from the downward things or like who knows, right? There are many things that
Yeah. So you could things that have been tried is to have some extract also some what we call site information from the audio, like we call quality measures. So for example, you have two embeddings and one have 30 dB SNR and the other has 10 dB SNR. You should weight more the one that has higher SNR, right? That would be one possibility, but in general, what works best is just taking the average. In most cases, any fancy kind of model that you use is not better than the simple thing of taking the average. Yeah. Yeah. Speaker verification.
The recording can or cannot be contained in the training, right?
So all the success are disjoint. So the enrollment recordings are not included in the training, and the test recordings are not included in the enrollment or in training. So all the data is completely disjoint. Yeah. So usually, and also the speakers are disjoint. So in the speaker verification, the speakers that you use in training are not included in the enrollment or test phase. So these are a different set of the speakers, completely different set of the speakers.
Why is it that?
It's
why is it that there is?
It's because that's the most realistic condition. So let's say that you want to commercialize some kind of this technology. So the company will create the model using some speakers that they will record somehow, right? And then you will sell the system, and whoever that buys that system will only have access to these two phases. So you will be able to enroll new speakers, for example, their employees in the system, and then we'll have the test phase where also will be the employees from the company that's buying the system and the imposters. And the imposters, the imposters could be here because you don't know. It can be anyone, but in principle, the most fair way of evaluating the system is having these young groups, because if you have one speaker that is in enrollment or test phase, in the training phase, this speaker will be so the system will work better for speakers that were included in this in the training. So because in the speakers that you have in the training, also you have more than one audio per speaker. And here usually what you use just one audio in enrollment and audio in test. So you try to see how your system will behave when you have very few audio from the enrollment and test speakers. And if you have these speakers there, you will have lower equilibrium rate, but that will be over optimistic because usually in reality that's not going to happen. Okay. More questions? Okay, so before deep learning, we have the first method that was used to extract embeddings from audio were I-vectors. So we can see very briefly how I-vectors work. So when we have I-vectors, we still have the audio, and from the audio we have some sequence of the spectral features. And then what we do is we model these spectral features using a mixture of Gaussians. So mixture of Gaussians is a model where basically the models the probability distribution of the features, assuming that each one of, so suppose that you have the feature for this interval, the feature for this interval, and so on. And then each one of these features is going to be generated by one of the Gaussians of the model, right? So this feature will be generated by a Gaussian here, and these three features will be generated by another Gaussian here, and maybe these two will be generated by another Gaussian here, right? So then what we do is for each audio, we are going to train, we are going to assume that each audio can be modeled by a Gaussian-Mister model. But the means of this Gaussian-Mister model is going to have some restrictions. So we are going to take the means of this Gaussian-Mister model, and we are going to concatenate it into a super vector, and we are going to call it uppercase M. And this super vector is going to be equal to another mean vector that is called the universal background model mean. So basically, it's the mean of a GMM that is not specific for any audio. It's like the average of all audios. Plus a T matrix that we call total variability matrix, that is a low rank matrix. For example, this T matrix will be, so if we have here the super vector of an audio, then we have here the utterance independent super vector mean, and then we have the T matrix that will be, in this case, will be 6 times 2. So basically it's a low rank matrix because the number of columns is much smaller than the number of rows. And this is multiplied by some latent variable W, that was what we call I vector. So with this formula, the possible values of the super vector mean of the utterance are restricted by W, so depend by T and W, right? So if I want to know what is the mean for a given utterance, what I have to do is estimate what is the W1 and W2 for that utterance, and not all possible means will be allowed, right? Basically, this means will live in a subspace which is defined by the columns of the T matrix. So we can here see an example, visual example. So let's suppose that here we have the Gaussians corresponding to the utterance independent model. So basically, this is the Gaussians corresponding to the universal background model mean super vector here. Now, assume that we observe, so as now we can see what are the directions where the first column of the T matrix is going to allow us to move our means. So basically, T11 and T21 will allow me to move this Gaussian in this direction only, based on W1. Then T11 and T21 will allow me to move this Gaussian in this direction, and so on. So now, suppose I observe this data. So this is the data from my test utterance. So now what I'm going to do is I'm going to modify W1 to make these Gaussians closer to the actual data. So you can see here that the data is at here, but still this Gaussian cannot move to the data because the movement is restricted to be in this line, right? So when I increase W1, I get closer to this data, to the data, but not enough. So now that I move the data based on W1, I can go to W2, and we can see that the second column of the T matrix allows me to move the matrices. Sorry, the second column allows me to move the Gaussians in these new directions, right? So by increasing the value of W2, I can continue making my Gaussians closer to the data. So now, this new direction allows me to move the Gaussian from here to actually where the data is. Something that that is useful from this model is that, for example, it allows me to move Gaussians that doesn't have any data or very few data in the test utterance. So for example, this Gaussian only have one sample in the test utterance. So if I don't use this kind of model and I just estimate this means by regular maximum likelihood of a Gaussian mixture model, this Gaussian will be badly estimated because it doesn't have data. But with this model that has, let's say, restrictions, this model defines how speakers actually, how the Gaussian mixture models of the speakers actually behave, right? And this allows me to actually get good estimation of this mean supervector, of the attendance mean supervector, even having very few data in the test attendance. Okay. Any question? Yeah.
Could you clarify what the different Gaussians were in the first place? And
so different Gaussians usually mean different types of phonetic units. So for example, you could have one Gaussian per phoneme, but actually we usually what we have is more than one Gaussian per phoneme, but we don't really use a phone detector to assign samples to Gaussians. We just trying to first a general Gaussian mixture model that we call universal background model, and with that we just throw a lot of data to that model, and we just train that model by maximum likelihood, and we set the number of Gaussians to 2,000 or 4,000, and that is enough, right? So, and then and at evaluation time, what you do is you just take your spectral features and use the GMN to calculate the posterior probability of a feature belonging to one Gaussian. And usually that's more or less, that's almost a hard decision. So basically, you will say, okay, this feature belongs to Gaussian 1, this feature will belong to Gaussian 2, and so on.
Is this calibrating based on a new utterance that you get? Like, oh, this is how this person pronounces their O's and their their O's, and that is you adjusting the Gaussians to like better represent the data, or am I understanding?
Yeah, so you first train this Gaussian mixture model with all the data, and then you have to train this T-matrix based also on the data. And in that way, you get a model that tells you how utterance, how the GMNs of utterance actually behave. And then for each new audio, you what you do is given the T-matrix, once you already train the T-matrix, you just fix it. And then for each new audio, what you do is calculate the values W1 and W2. And that's actually what defines, and from W1 and W2, you could calculate where the Gaussians for that utterance are. But actually, we usually don't care about that. We just care about W1 and W2 because that's my embedding that I'm going to use to do a speaker recognition later. So actually, you don't really, at test time, you don't really care about what is the position of the Gaussians. You just care about W1. Okay. Any more questions? Okay. So when you to calculate W, what is the I vector? What you do is you use the Bayes theorem. Basically, you have a likelihood function that is basically the product of a product of Gaussians. So basically, for each Gaussian, and then you do the product for each Gaussian, and then the product for each time step of that are in for each Gaussian k, and then for each time step that belongs to Gaussian k, you have a Gaussian that is that has a mean that is equal to mk plus tkw, which basically is the this is the mean and the T-matrix that is in the block k of the matricial equation. So basically, if you are in Gaussian 1, that will be M1 will be these two values, and T1 will be these two rows, right? So you have this likelihood function, and then the I vector also has a prior probability distribution, which is just a standard normal. And then if you want to calculate the I vector has a posterior probability distribution that is also a Gaussian that is going to be given by this equation. So first you have L, that is the precision of this Gaussian, which is equal to the identity. This identity comes from this prior. And then you have this term that depends from NK. NK is the number of features that were assigned to Gaussian K. So depending on how many samples are for each Gaussian, you will have a different weighted average here. And then the mean of the Gaussian, of this Gaussian, basically what we call at the end the I vectors, that is what we are going to actually keep, is L-1 also multiplied by the sum of Tk sigma K minus 1, and then F hat K, which is what we call the centered field order sufficiency statistics. Basically, is the sum of all the Fk is the sum of all the features that were assigned to Gaussian K, but centered in the mean of the UVN. So basically, you take the acoustic feature, you subtract the mean of the Gaussian that has been assigned to, and then you sum all the features that were assigned, or the centered features that were assigned to Gaussian K. And those are the two, basically what we call the sufficiency statistics. So with NK and FK, you can calculate the I vector. Okay. And then to calculate the T matrix, what you will use is the expectation maximization algorithm. So what you do is you initialize NK and sigma K with the universal background model means, as I was explaining before. You randomly initialize T, and then you iterate to estimate T. So basically, you compute the I vector posterior given the value of T in the current iteration, given the so you get the I vector posterior for each utterance in the dataset, and then you use this I vector posterior to calculate the expectation maximization objective. It's basically the logarithm of the likelihood of the data given the T matrix, given the posteriors that we calculated in the E step. And we just maximize this, and this has a closed form solution. But now you could just write the Q formula in PyTorch, and it will calculate the derivatives for you, and you can iterate using gradient descent. But this has closed form solution. So I'm not going to go much into this. So some takeaways from this part is that I vectors were the first approach using embeddings for speaker recognition. This is a generative model, and we will see more about how to generate. So basically, it's a generative model because as it is a probability distribution, you can sample data from the model. So you can, once you train the model, you can generate synthetic data using this model. And this is a method that is unsupervised. I don't need speaker labels to train this model. Any questions? Too far? No? Okay. So now let's see more about neural embeddings. So there has been several approaches of neural embeddings that have been tried in the literature. One of the first ones that were tried was Siamese networks. So basically, Siamese networks, what you have is you have one network, or you can say let's have two networks, but that have tight parameters. And then what you do is you take your training set, and then you divide the training set and enrollment utterance and test utterance. And then you pass those utterances through the DNN, and then you compare both. And here you have to create, let's say, target trials and non-target trials in the training set. So you just minimize the loss, the binary cross entropy loss here. And this basically this binary cross entropy loss will be the logarithm of the posterior probability of having a target trial, which will be the sigmoid of this L value. So basically, in this word, they use this formula for the L value, but actually what is important is just the first part. Basically, this is just like calculating the cosine scoring between the enrolled utterance and the test utterance. And then you minimize the binary cross entropy loss function. So basically, you minimize the minus posterior probability of target trial. So you have two parts in this formula. The first part is the sum over target trials, and the second part is the sum over non-target trials. So basically here you had to maximize the posterior probability of having a target trial. And here you had to maximize the posterior probability of having a non-target trial. This was basically 1 minus the probability of having a target trial. And this method did not work that well because it needed a lot of speakers to be able to do better than I-vectors. So here we have I-vectors trained with 5,000 speakers, and DNN model trained with 5,000 speakers, and here we have the model trained with 100,000 speakers. And this method, to be able to get a significant improvement over I-vectors, needed actually to train with way more speakers, with at least 15,000 or 100,000. And the reason why that happens, we think that is because of the vanishing gradient of the sigmoid. So here we have the formula of the sigmoid in blue and the sigmoid derivative here. And these are the score distribution for target trials and non-target trials. So you can say that once you have started training and your model has started to converge, most of the trials that you use for training are in this area or this area where the derivative of the sigmoid is almost zero. So when you use these trials to train, you don't generate gradients. So your model doesn't move. Only the trials that are here in the middle are the ones that generate gradients. So basically you are wasting a lot of computation when training with this method, because most of your data that you are putting in the neural network won't generate the gradients and won't actually move the weights. Okay. Yeah. Full, I think it's the average of all the rows. Yeah, I think so. This is full audio. This is different test lengths. So another method is the triplet network. So here, they try to do better than with the sigmoid network. So the scheme is the same. You have one network where you pass enrollment trial and test trial, but here instead of having two trials, you compare 3 trials. Sorry, instead of comparing two audios, you compare 3. So you have one audio that is the anchor, and then you have one audio that is a negative sample, another one that is a positive sample. So the positive sample is from the same speaker than the anchor, and the negative sample is from different speaker than the anchor. And then you have this formula that basically what it does is to pull the negative sample away and to put the positive sample closer to the anchor. And you enforce that at least you have a margin alpha between the positive and the negative sample. So the negative sample has at least to be alpha times farther from the anchor than the positive. Okay, so that helps you to get a more discriminative model. However, it has a similar problem as the Siamese network. To train this model, you need to find hard positives and hard negatives. Because if you have easy positives and easy negatives, you have the same problem as before. Many of those trials won't generate gradients. So that means that you have an extra complication here, that is, you have to first you have to train a first version of the network, and then you have to use that version of the network to find hard positives and hard negatives. So, or you have to somehow find a strategy to do that, to select online hard positive and hard negative to train the network. So instead of that, in this vector paper, the proposal was to just, doesn't work? Oh, this. Okay, thank you. So in this vector paper, the proposal is to have a network where you have this encoder encoder part where you have given the input features, you get a sequence of output features, then you have a pooling layer, and then you have a classification head where just the output are the speakers in the training set. So you have one neuron in the output for each speaker in the training set, and then you just train it using cross-entropy loss. And this was much more simple than the previous approaches, and actually it ended up working better than triple loss or than CMS network. So the only thing that we need to take into account is that so when we compare with I-vectors, is that these neural network models needed more data to be trained than I-vectors, but we could compensate that using data augmentation. So when we have systems without data augmentation, here in the first column, we have more or less the same result for I-vector or for different flavors, for I-vector or for S-vector, right? But when we add data augmentation, when we try the S-vector, which is here, S-vector start doing better than I-vector. And here we were using a small number of speakers, and when we have, let's say, new databases with more speakers, then the difference between I-vectors and S-vectors were larger, and I-vectors become kind of obsolete. Okay. So yeah, so the takeaways here is that semis and triple networks were difficult to train because of vanishing gradient problems and the difficulty of doing hard negative mining, and that currently state-of-the-art approaches use S-vector scheme. Any questions? Okay, so we are a little bit late in the schedule, so let's go to neural architectures. So the first S-vector model used time-delay neural networks. So basically, time-delay neural networks is another name for one-dimensional dilated convolutions. So dilated convolutions, what will you do is you assume that you know what a convolution is. So what you will do is to try to increase the receptive field of your convolutional network. What you do is to delay the kernels. So basically here, for example, you have the input in the bottom, and here you have a kernel that has size 2. So basically, but so you to get the output at the next layer, you use these 2 points, but you don't use the central point. Basically, that means that the convolution has a dilation of 2. When the convolution has a dilation of 1, that means that the convolution has a dilation of 1. Basically, it's the same as saying that there is no dilation, and you will use these 2 points to calculate the output. If you have a kernel 2 and a dilation of 2, you will use these 2 points to calculate the output. So that means that using a small kernel size, you can have a larger receptive field, right? So for example, here you have a kernel of 2 with a dilation of 2. Here you have a kernel of 1. And then here you will have a kernel of dimension 3, but you have a dilation of 3. So you skip these 2 points. And here the same, you have a kernel of 2 and a dilation of 2. And then you just use these 2 points to calculate the output. So what we expect here is, even though each convolution that doesn't use all the data, at the end, all the data is used, because I don't use this point to calculate this output, but when I calculate this output, I do use this point, right? So at the end, it's a way of making my network more efficient and having larger receptive fields in the total network. So basically, the total receptive field of the network will be, let's say, the sum of all the kernel time dilations that I have along the layers, right? So after that, we have the standard TDNN. With the standard TDNN, you just take the TDNN block, which is dilated convolution, batch normalization, and ReLU, and then you add some extra block which have a convolution with kernel 1 plus batch normalization plus ReLU, right? And that gives a little bit more improvement. And then we have something that we call factorized time delay neural network. So to try to make the network deeper and have, let's say, less parameters, what we do is we take the matrix weight matrix of the convolution, and we factorize that matrix into the product of two matrices. Okay, so we take the convolution matrix and we factorize that into the product of two low rank matrices. Okay, so in this manner, we can have less parameters, and we can make the network deeper. Also, we can include skip connections. So we take the bottleneck here, and we concatenate the bottleneck, for example, in this layer. So as we use the bottleneck for this concatenation, also we save parameters, because the dimension of the second convolution is going to be the sum of this feature plus this feature times the output. So if we concatenate features that are coming from the wider part of the network, we're going to have more parameters, but if we do skip connections between the bottlenecks, you have less timing parameters. This is similar also to dense net in computer vision. Okay. Okay, we'll skip this. These are some results from the NIST evaluation SR18, and we got like the best result here using the factorized 3NF model. And that model has 17 million parameters that right now, today, may look very little parameters when we have networks of 300 million parameters or billions of parameters. But in that time, were networks that were considered very large. Then we have also vector models that are based on two-dimensional convolutions, and basically assume that somebody needs to know what a two-dimensional convolution is, or can we skip this one? Okay. So basically, you have models that are based on, instead of one-dimensional convolutions, two-dimensional convolutions, and with these models we can create very deep residual network models. So basically, a residual network have a scheme like that. You will have an input where you have the spectrogram, and when you train it with batches, basically the dimension of this will be batch times one channel, and you have height and weight, but in speech, height will be the frequency dimension of the spectrogram, and time will be the width of the spectrogram. Okay, so you have first 3 blocks where you increase the number of channels from 1 to 64, and then you have several blocks here, and each time you switch this group of blocks, you do a downsample in frequency dimension and time dimension. So at the end, your feature maps are downsampled 8 times in the output. And then each one of these blocks you can substitute by, let's say, the basic residual blocks, which are 2 3 times 3 convolutions, or you can use what is called the bottleneck block, where you have 2 1 times 1 convolutions and 1 3 times 3 convolution in the middle. And when you use the upper one, what you get is a ResNet 34, basically a ResNet with 34 layers, and we use this one, you got a ResNet 50 layers. And you want something more advanced than that, we have the rest-to-net block. So if we use the rest-to-net block, you can have something with larger receptive field. So the rest-to-net block will take the regular bottleneck block, and you will do first the 1 times 1 convolution, basically just a rotation of the channels of the feature maps. And then what you do is you take the channel dimension and you split it into several sub-blocks, several groups that we call, and the number of blocks is called the scale. So for example, here we have divided the channel dimension into 4 blocks. So the first block is just copied in the output the same, without changes. The second block passes through a 3 times 3 convolution, and then is added, is put in the output, but then is added also to the third block. So this again passes through 3 times 3 convolution, and is added to the next block, and so on. So that means that each one of these groups is going to see a different receptive field. So the first one will have a receptive field of 1, the second one 3, 5, and 7. And you increase the scale also. Sometimes 4 is used, sometimes 8 is used. You can have larger and larger receptive field. So you accumulate the whole receptive field of the network. So for example, ResNet34 will give you 2.4 seconds of receptive field. So each output that you get from a ResNet34 is calculated based on 1.2 seconds in the future and 1.2 seconds in the past. And then if you use a RES2net of 50 with scale 8, you are looking at 4 seconds in the future and 4 seconds in the past. So you are increasing the receptive field, and usually when you increase the receptive field, you get better results. Also, in the output of this block, you can add what we call squeeze excitation. Squeeze excitation is a method to then, after you have the output, is to decide which channels are more important than others. So basically, this block, what it does is calculate a scale between 0 and 1 that you use to multiply your channels. And this is just done by taking your features, your feature maps, and then you take the average over time of those feature maps. And then you apply a fully connected layer, a ReLU, and then fully connected layer. Basically, this creates a bottleneck. Then you have a ReLU. Then this fully connected layer go back to the dimension of the original feature maps, and then you apply a sigmoid to transform that to a number of between 0 and 1. And then this number is multiplied by the channels, and then you can decide which channels are more important and which channels are not important. So another network that came up later was ICAPA-TDNN. Basically, ICAPA-TDNN is a RES2net network, but using one-dimensional convolutions. It's kind of a mixture between TDNN network and RES2net network, because in the ResNet network, 2D ResNet network, you have these downsampling steps that are used to increase the receptive field. And here, there are no downsamplings along the network architecture, but you have dilation in the convolution. So basically, this network replaces downsamplings by dilations. So you have dilation 2, dilation 3, dilation 4. And then there is one of the basic block. It's basically the same as a RES2net block, but using 1D convolutions instead of 2D convolutions. And we will implement one of these in the lab later. However, even this ICAPA-TDNN has been quite popular in the last years. Still, RES2net was given better result in our participation on the NIST speaker recognition evaluation 21. So still, I prefer two-dimensional networks that usually given better result than one-dimensional networks. Okay, then we have so recently, or not so recently, this self-supervised model like Wade2Vec came out. And then usually, so you can train these models, and then you can use this model as feature extractors for all kinds of tasks, right? So for example, we have Wade2Vec2, and the way it's trained is, yes, you have the audio, and then you have some sequence of convolutions that are kind of the equivalent of the MEL filter bands, but trainable. So basically, this convolution will use some kind of feature here. And then you have a vector quantizer that is trainable too, that is differentiable. And then, so basically, you get some feature from this convolution, you quantize it, and then you, for example, mask this feature, and you train the network to predict the quantized value of this feature that has been masked. And that way, you train these huge networks using a lot of data and a lot of GPUs, and then you can use these networks as feature extractors, right? And then you have Hubert, which is almost the same. Yes, instead of having a vector quantizer that is trained at the same time as the network, what you do is you have multiple steps in the training. First, you get the audio, calculate MSSC features, and then you quantize them, and then you train this transformer to, you also, again, you mask some of them, and you train this transformer to predict these ones that have been masked. And then you train this for some time, and then you recompute features from the train model, and then you quantize them with k-means, and then you continue training this with the new features, and then you do several steps, right? And then for using this scheme, we have Huber and WebLM. And the difference between Huber and WebLM is that WebLM, besides doing that, also do very heavy speech augmentation using noise and overlap speech. So the WebLM model is more robust to noise and also is better for speaker recognition in general. So once you have these weight-to-weight models or WebLM models, you can put some, let's say, some head model, some kind of decoder model on top of the transforming model. So usually in this WebLM model or weight-to-weight model, the best features for speaker IDs are not the features in the last layer, so some features in the middle layers. So instead of finding out which one is the best layer for speaker ID, what is best is just you take all the layers and you do a weighted average, and you train these weights. And at the same time, you can train a kappa TDNN model on top of this. Usually you take this weight-to-weight model, WebLM model, you train this weighted average and a kappa TDNN of 3 layers, and you use this to extract embeddings. So the way you will do it, you will have to do it in several stages to avoid overfitting. So first you keep this model frozen, and then you train this kappa TDNN and the alpha weights. And then you do another step of where you fine-tune both the kappa TDNN model and the weight-to-weight model together. And then you do an extra step where you do, let's say, a training step where you, let's say, use some tricks to make the task more difficult, like increasing the margin that we will see later what it is, and do also some hard negative mining, and then we make the model more robust. And we can see here that WebLM large can do much better than a kappa TNN, for example. Okay, so some takeaways from these SVETOR architectures is that, so we have a SVETOR encoder that computes a sequence of speaker discriminant representations, and then we have architectures based on 1D and 2D convolutions and also transformers. But base architectures are rest-to-net with 2D convolutions, a kappa TDNN, which is a rest-to-net with 1D related convolution, and also weight-to-weight to style models, which when combined with a kappa TDNN. Those are the best models. How much time do I have? 0. Okay.
Is that okay? Let's see.
Oh, I have a lot more.
So that's the problem with Jesus. Next.
But I can continue in the lab time.
Okay. I'm of course very excited to be here because I, did my PhD at Johns Hopkins, and I participated in multiple JSALT workshops. The first one I did was exactly 10 years ago, and it was the first one with the Jelinek memorial name. So of course, getting to give a summer school talk is pretty cool. And today I will be talking about speech enhancement and diarization. So to give a kind of a brief overview of what are all these tasks? What are they about? It's towards the cocktail party problem. So the cocktail party problem was introduced more than 70 years ago now. Basically the idea behind the cocktail party problem is that, say we're in a cocktail party where there's, multiple conversations going on kind of concurrently, and you want to be able to understand what's going on and what people are talking about. So this deals with, multiple people speaking, and there's noise and a lot of stuff going on, and people can even be talking at the same time. So kind of everything I'm talking about today is kind of directed towards bringing speech technology to being able to address these sorts of problems. So the first thing I'll be talking about is speech enhancement, and separation is kind of a subtask of this, but kind of its own thing. And I'll be talking about that as well. So to start things off, what is speech enhancement? And one thing with speech recordings are that they often have a lot of degradations and interfering sounds. Like if you think of what a recording of speech sounds like, you probably are used to something that sounds like this.
We continued driving past industrial parks and suburban sprawl until finally.
But that's a kind of a, maybe not a studio recording per se, but it's using, professional equipment that's been, cleaned up and edited, and it sounds like very nice. But if you actually were to listen to raw audio from a recording that's just a microphone placed in a room, it can sound something like this. And see, like that's much harder to understand. Like for example, hot sauce was spoken in that clip, as well as hipster. And if any of you heard those words in that, I'd be shocked, because even if you know they're there, it's really hard to find them. But of course, that is kind of an extreme example. So this third one is maybe a little more realistic.
It's called Space 1026. It's galleries and studios.
And so in this instance, it's not quite so bad. The microphone is further away from the person, so it's a little quieter relative to the noise in the room. And then you have like an air conditioner, but nothing too extreme. And so speech enhancement is generally kind of the task of taking these recordings that have maybe, multiple people talking, noise in the background, reverberation, and we want to produce a new recording that is just the target speech without any of that interfering stuff in it. So why do we even care about this task? Particularly since in this case, we're producing actual waveforms. And one reason is that human listening can always be the end goal. So, we talk a lot about, speech technology, and we're trying to kind of process information, transcribe speech, whatever. But sometimes you just want to listen to it. So, for example, if you were trying to produce maybe your own podcast and you don't have, the high quality equipment, it would be nice if there was a system that could kind of clean up your recording and maybe take something that sounds like that third recording and make it more like the first one. Then, of course, as you might expect, degraded audio can lead to degraded performance of downstream systems. So if you have something like a ASR system that's transcribing speech and was really only trained on kind of high quality speech, it's not going to work as well on the noisy stuff. And so maybe you want to train a system to kind of clean up audio and improve the performance of those systems on that type of data. And then the third point is that even if we don't necessarily run a speech enhancement system as part of a pipeline, a lot of the research that's developed within the speech enhancement kind of research field will then be integrated into later technologies. So for example, if we are doing something like trying to train an ASR system that works in noisy environments, maybe we're going to do something like just data augmentation, but we also might, change our architecture and kind of integrate some of the techniques that were developed in speech enhancement into kind of an end-to-end system. So one of the kind of fortunate things about the speech enhancement math is that it can often be very, very easy. So in this case, kind of like the input to our system is going to be the sum time domain signal x of t that we're modeling as simply the sum of s of t, which is going to be our target speech, and n of t, which is just all the interferences. And then what we're trying to do is output y from our system, which is simply an estimate of the s. So you can kind of think of this as either trying to estimate the s or maybe remove the n. And then you can treat things a little more precisely. So for example, reverberation is usually modeled as a convolution, and that's not 100% accurate, but it's close enough. Yeah. We'll get to it. So separation, for example, we can say maybe our n is not noise, but is maybe another speaker. And then you can kind of combine all these formulations together. So in this final equation, we have kind of a sum of multiple sources that each have their own kind of reverberation applied. And then we also have noise sources that can come from multiple different noise sources as well. I'll also talk a bit about how we kind of evaluate these systems. And the two main ways that we evaluate them are with kind of full reference algorithms or no reference algorithms. So when we talk about full reference, what that means is that we basically have kind of the ground truth. So you have, the clean speech, you have, the noisy speech, and you run your system that removes the noise. And now you're able to compare that to the clean speech. And this is kind of like what your typical, like how typical metrics are computed. And I have these two categories here. So SISDR is kind of like the most common one from this category, but SNR, SDR, SIR, these are all like basically signal to noise metrics. So you have, they're evaluated in decibels, and it's basically going to be, in some sense, the like power of the target signal to the power of the interferences. Then PESC, STOI, and Polka are not decibels. They're generally trying to emulate something like the mean opinion score of the no reference type thing. So to move on to that one, if we don't have the ground truth, something we can do is just listen to it. So this is kind of the easiest way to evaluate the output of the system if we don't know what the kind of ground truth clean speech is going to be, is you can just get people to listen to it, give a score on 1 to 5, and then you can take the mean over all of your subjects, and that's how you can get a score. And so that's one of the things that people try to then emulate with a full reference metric as well. Then there are some additional like non-reference metrics. I've listed some here, and I can't really tell you anything about them because it's not something people do too often. Sometimes they're kind of signal processing, like designed, where people have tried to like actually design a metric that evaluates the quality of the speech. But then there's also ones where people try to, say, train a neural network to kind of predict what a full reference metric would do on a recording. And I will say that although these types of evaluations are quite rare, and because they have a lot of problems, more recently there has been interest in it because there's been a lot of like interest in generative models. And so if you're kind of generating enhanced speech that is not necessarily the precise original like clean waveform, you can't use the full reference algorithms. And so people want to find ways to evaluate the like generative outputs. So there's been a push like in really the last year to try to develop kind of better no reference evaluation metrics. And then of course, a third thing you can do is always evaluate the system, your speech enhancement system, via some sort of downstream task. So if you're trying to clean up speech and you have, maybe an ASR system that's trained to only work on clean speech, you can always just say, well, we take a bunch of speech, we run our system on it, run the output through the ASR system, and we can kind of evaluate how good our enhancement system was based on the kind of relative performance of the ASR system. Oh, yeah, and here's a kind of this is the equation for SISDR, which is again kind of the most common metric. And so again, looks very similar to a basic like decibel calculation. And then the SI actually stands for scale invariant, which is an additional trick where you say that you kind of are trying to rescale the system output to match the like ground truth waveforms. And one thing I really want to emphasize is that the ground truth is really, really important for this task. So if we think about something like ASR, it's very easy, more or less, to kind of transcribe speech by like a human can do this task. So if you have a bunch of data and you want to have ground truth for ASR, you just have to get people to listen to it and figure out what was said. But if you have, say, noisy speech and you want to know what that speech sounds like without the noise, you can't do that. Like that's not something that someone can actually do. Like that is the task that we're actually trying to train systems to do. So like you can't really like generate ground truth from speech that's already noisy. So it's, as a result, it's like very, very common to use kind of synthetic data. So what you're doing is you're taking something like clean studio speech and you're actually artificially adding noise. That way you actually have the ground truth of what the like clean speech sounds like for a given noisy recording. And part of this is like, it's important for evaluation because again, we generally are trying to use the full reference metrics. So you need to use synthetic data if you want to evaluate those metrics. But also neural networks are basically always trained to have, the ground truth as the target. So neural networks are also almost always trained on synthetic like noisy speech. And this is a big deal because there can be domain mismatch, where if your network is only trained on synthetic noise, you can never train a system on like in-domain recordings because you never have ground truth of any sort of like realistic condition. So there can be issues with kind of like this domain mismatch and a lack of robustness. And then, so one thing people do try to do, like practically speaking, is avoid trying to learn the waveform directly. So for example, if you are trying to train, again, an ASR system that operates on noise and you want to integrate a speech enhancement system, it may be better to not actually have that intermediate step of producing a waveform because there is that issue of ground truth. So like if you kind of stick two models together and never compute a loss on the middle, you can then like adapt that system on the in-domain data. So just to talk about like the general approach of how we do speech enhancement, it all kind of, almost all kind of falls in this category of filtering. Yeah.
Like like of internal representation, which is exactly an audio representation. So the first part of the model would learn, hopefully, then I think the other part would be the ASR model. Because you can take them together and make it a black box. But we can make it two black boxes and make the internal representation have the same structure as an audio recording and hope that maybe the first model learns the denoising. Does that work?
I mean, yes, it does. Yeah. Yeah. Like I can't really like think of any particular examples, but it is something that works, and there's always just questions of, different systems are going to perform better or worse in kind of different conditions. But that is something that people do. Yeah, so back to the general approach, like basically everything falls under this category of filtering, which is like a really broad and nebulous term. And similarly, there's this distinction between like temporal filtering or spectral filtering. So are we trying to operate in the audio domain, or are we trying to operate in like an STFT or a spectrogram? And estimation versus decomposition is another categorization where you can say, are we trying to estimate like maybe the speech signal directly and remove everything else? Or are we trying to decompose the audio and say, well, we know that it has speech and noise, maybe we can kind of split it apart into those two categories. But all of these distinctions are somewhat arbitrary, and you can kind of always formulate things one way or another. So one approach I did want to highlight is mask-based enhancement. So in this plot, this first row is kind of an example of a spectrogram of speech without and with noise. So the top left is kind of like a clean speech spectrogram, and then to the right of it is the same spectrogram, but now there has been noise added. So you can see that there's just like a lot of energy all over the place, and it's harder to see like the actual speech within that. But one of the fortunate things about the short time Fourier transform, which is what we use to generate these spectrograms, is that it's actually an invertible transform. So you can go back and forth between the waveform and the spectrogram. So one thing people do, which is this mask-based approach, is you can kind of say, when we have a spectrogram, if we can try to classify every bin in the spectrogram as either belonging to the speech or the noise, you can simply mask out any of the bins that are containing noise. And then when you reinvert it, you've actually removed the noise from the audio. And so that's kind of like how the mask-based approach works. And then this third line is kind of the regression extension of that, where you can say you can either classify each bin as belonging to either the speech or the noise, or you can say it could be somewhere in between, because these things do actually overlap. So you can kind of have a soft decision and say how much of the bin is contained, how much of the bin contains each of the two sources. And so this is a very popular approach. Then I also wanted to make some comments on the other approaches. And unfortunately, with speech enhancement, a lot of the times they're completely unrelated signal processing approaches, or even the neural network approaches can get kind of uncategorizable. So there's no easy way to kind of put them all in a category and say, wow, people do this. But I'll kind of give you this brief overview. So one thing is they can be learning free. So there's not even any parameters in your approach at all. Another approach is unsupervised, where maybe you've designed some algorithm that does have some parameters that describe kind of like the underlying signals, but you're not like training it on any like data. It just learns it from the data that it's running on. And then finally, supervised is kind of like the neural network case, where we have a bunch of parameters maybe, and we're trying to estimate them from some training data and hope that it transfers to the kind of like test time data. And then some things people do, you can kind of like estimate like speech presence probability. So say, what is the likelihood that, an STFT bin is going to have speech? You can kind of estimate like the distribution of the noise, maybe the signal to noise ratio, the power spectrum of the speech. Like there's a lot of different things you can kind of estimate and approach these problems from. And then I also wanted to kind of call out non-negative matrix factoration and independent component analysis as two kind of traditional pre-deep learning methods that were popular. So non-negative matrix factorization is one where we're trying to kind of decompose the spectrum into different sources. And then ICA is a kind of stochastic model where we assume that we have these multiple signals that are being mixed. So next I'll touch on reverberation. So to kind of explain what reverberation is, if you're completely unfamiliar with this term, this is kind of like the echo you get in big rooms. And the way this is kind of modeled is that we have kind of these three kind of components of the reverberation. So the first thing is going to be the actual like direct path. So if somebody says something and it goes directly to the microphone, that is like the direct path. And that's kind of like what you want. You don't want anything else beyond that. But we have the early reflections, which is to say that like, if I say something and it's collected by a microphone, the microphone is also going to hear the same thing a little bit later because it, bounced off that wall and then reached the microphone. But that's happening with all of the walls. And so that's what the like early reflections are. And then finally, we have this kind of third stage, which is the late tail, where things don't just bounce off one wall and then reach the microphone. They actually just keep bouncing around. And so we get more and more of these reflections, and you get kind of this tail where you don't really see the individual reflections as well, but you just kind of get this more stochastic random, combination of the energy that was in the original speech. And then in terms of how this affects the actual signal itself, here's again two spectrograms. The one on the left is clean speech, and the one on the right is with reverberation applied. And as you'd kind of expect, there is kind of like a smearing effect in the time direction. So you see anywhere there was energy in the original speech, you kind of see slightly less energy to the right of that, and it kind of decays. But it also actually does smear in the frequency domain as well. So you just kind of get this like overall blurring of the speech spectrogram. Okay, so in terms of how people de-reverberate signals, one of the most popular methods by far is this weighted prediction error de-reverberation algorithm, which interestingly enough is actually a signal processing method and does not involve neural networks at all. And basically the idea here is that you can kind of predict the late tail based on a linear combination of the like previous observations. So as you'd kind of expect, like Since we're just seeing like delayed and attenuated versions of our original signal, you can predict those based on the like prior observations. And that's kind of the idea behind the weighted prediction error algorithm. And one kind of trick it does is that it does not try to cancel out the early reflections. And one benefit of this is that it kind of minimizes any degradation you do to the original signal because you're only trying to remove the late effects. But also the early reflections can be very like geometry dependent. So even as if I'm walking around this room or even turning my head, like the exact path of the reflections changes. And so it's not going to be the same filter like all the way through. And so WPE doesn't try to kind of cancel out that part of the signal. And then I'll also comment that people have tried to extend this to kind of neural methods as well, and they're successful to varying degrees. But basically, since part of the WPE algorithm is estimating the speech like presence, like the power of the speech in any given point, you can estimate this using a neural network, and it kind of works better, but then starts to have the issues of the generalizability. So next I'll talk about speech separation. And I'll play some clips of this because it's always fun to listen to and it's my favorite thing. So basically speech separation is rather than taking speech with a bunch of noise added, we maybe have multiple speech signals and we want to actually produce both speech signals from the single mixture. So here are some outputs from a system I trained recently. The first clip is the input mixture.
Did a dream, you know, it's just to get on a bus. I remember our first bus on our first tour in '83, where we sat.
Here's one of the outputs.
It was the dream, you know, it's just to get on a bus. I remember our first bus on our first tour in '83, where we sat.
And the second.
Did it with these people because I know that their view on their faith is so much.
So I always think those are really cool to listen to. Seems kind of like magic to me. But basically, the reason you can do this at all is that speech is generally pretty sparse in the spectral domain. So again, I have more pictures of spectrograms, and these are actually pretty much raw STFT magnitude. And you can see that like the speech signals are kind of just, you see the like lines of the formants, and so they don't overlap much at all. So it's actually fairly easy to kind of identify the two kind of speech signals even when they're mixed together. And just to briefly walk through the pipeline, it's very similar to the mask-based enhancement from before. So you'll maybe take an input speech signal, you're going to project it into some sort of spectral domain. Then you're going to have some neural network that is going to kind of take in this mixture and estimate masks for each of the sources. Next, you take these masks and apply them independently to the original input mixture and its spectral representation. And then finally, you can invert your spectral transform to estimate the speech of the two sources. So one of the big kind of challenges with speech separation and why it only started to be something you could do in the past, like, I guess, nearly 10 years now, is that these models are kind of hard to train with a neural network. And one of the big issues here is this permutation problem. And this shows up in a lot of other kind of related tasks, which is to say that if we have a mixture and we have two outputs, you don't actually have any reason to output them in any particular order. But if you're going to apply a loss function to them, you need to know what the ground truth is. And so the order matters in the sense that, like, if I'm going to have two ground truth waveforms, I have to give it to the network in one particular order. And if you give it in the wrong order from what it's trying to learn, you're not actually helping it train. And so there was kind of two approaches that both debuted basically at the same time to address this problem. And one is this deep clustering approach where you're essentially trying to estimate embeddings for each STFT bin, and then you can cluster those. And that way you don't actually have to estimate any particular source. You just have to like learn this affinity matrix that kind of maps which bins belong to the same speaker. Then the other approach, which has generally been much more popular since then, is permutation invariant training, which is to say, if you're not sure how to permute the system output with the ground truth, you can simply try all of the permutations, and whichever one has the lowest loss is probably the correct permutation, and then you only backpropagate from that particular loss. And of course, permutation invariant training with SISDR, the waveform level loss, is basically how all speech separation is trained right now. And then I'll also comment very briefly, there's a very related task called target speaker extraction. And this is kind of like a hybrid of speech separation and speech enhancement, where rather than saying, with speech separation, we'll have multiple speakers and we kind of want an output for each one of them. But in target speaker extraction, you have some sort of representation or sample audio or something for a given speaker, and you say, I want to separate this particular speaker out from any interfering speech and any interfering noise. And so it's a kind of a subtly different formulation, and the approaches are fairly similar to speech separation and enhancement. And next, I'll talk about multi-channel enhancement. So kind of everything we've talked about so far has mostly been assuming that you have a single microphone collecting your audio. But unsurprisingly, having more microphones helps a lot for doing enhancement. And part of this is that you're just getting more copies of your target signal, so you kind of just get more information overall. But also, depending on the geometry of the microphones, you start to be able to localize sources, which is very helpful as well. So I have one slide of math that's kind of nasty, but don't worry about the math, because this formulation can get pretty complicated. So this first equation that I put up here, so kind of we're modeling our input mixture X. This is no longer just kind of like a mixture of sources, but rather it's a spatialized mixture. So this is essentially an array of observed signals. So there's kind of like one waveform for each microphone, and we stack it into a matrix, say. And then this is, rather than a sum of sources, it's a sum of spatialized sources, because basically, if we have some target signal, like maybe speech, it's going to sound differently on each of the microphones, and it's also going to arrive at each of those microphones at a different point in time. So this concept of spatialized sources is basically what a given source sounds like as captured by a particular microphone. And then again, we have a sum over all of the kind of sources that are in the recording. And then we can break down the spatialized sources. One thing is they can be diffuse. So if you think of say an air conditioner in a room, you can't really say it's coming from any particular direction. If you were to record a room with an array and listen to each microphone, it basically just sounds like white noise on each of those microphones. And you can't say it's coming from anywhere. And so when we have that case, we kind of can only model this as these spatialized sources directly. However, if we have point sources that are actually coming from a particular place, we can then say that there is a kind of like a transfer function from when the source originated to each individual microphone. And this can be like a room impulse response, which is, for example, the convolution operation that we're talking about with reverberation that captures kind of like the room geometry and all the paths that happen. Or it can even just be a simple delay and attenuation based on how far the microphone is from the source. And then another detail is that we frequently approximate these things in the STFT domain. And since the delays between microphones are very, very small, we can basically say that the effect happens, the delay is smaller than a particular STFT window, and then it manifests only as a phase shift. So that means that rather than having to worry about something complicated like a convolution in your spectral domain, you basically can just have these spatialization filters, these A's, and you can just multiply them onto your particular STFT coefficients to spatialize them. And then one final concept in terms of the formulation is there's this idea of a steering vector, which basically captures the like directional information. So in general, when people are talking about a steering vector, we're saying given a particular array geometry, if you have a source coming from a particular direction, that manifests as the steering vector. So in the kind of first case, we have both like a phase shift as well as an attenuation based on difference. But a lot of times we kind of drop the attenuation because the kind of the decay of audio between being observed by two microphones is very, very small. So you can basically just say that a steering vector is kind of the phase shifts that correspond to a particular source direction. And so one of the main things people use with microphone arrays is beamforming. And just to give a very kind of brief conceptual overview of how this works. So delay and sum beamforming is like the kind of very basic thing to do, and people do it quite regularly. So like, let's say, for example, we have a person talking and a dog is barking. So we have two point sources that are coming from kind of different directions. So you can see in this like kind of diagram, the speech from the woman is arriving at the left microphone later than the one on the right. And vice versa is true of the like dog barking. So what we can do is if we delay the signal that we observed on the right microphone by the amount of time it took between those two arrivals, you can essentially align the speech signals from both microphones. And so when you add them together, you get constructive interference, and it makes the signal stronger. But in contrast, the dog barking signals, which were already out of alignment, are now even further out of alignment. So when you add them together, there's some combination of kind of constructive and destructive interference, and it doesn't really improve that signal. So now that you've like attenuated your speech and kind of reduced the interferences, you've kind of improved the signal overall. And one of the key parts of doing beamforming is actually estimating this time difference of arrival. That's kind of like the core issue with all of the beamforming algorithms. And just a couple quick comments on approaches. There's this GCC FAT, this generalized cross-correlation approach. And this is kind of a standard, more or less, cross-correlation where you're saying you're kind of adjusting the delay and you're trying to find a point when they match. And then MVDR beamforming is kind of an improvement over the delay and sum beamforming. And so kind of the short explanation of this is that it's a way to do beamforming in the spectral domain based on just an estimate of your target signal. So this is really amenable to, again, kind of like neural network approaches where maybe you can estimate where the speech is in a spectrogram, and then you can use that estimate to then do beamforming. So that's it for the speech enhancement half of this talk. Does anyone have any questions? Okay.
Was like the activities don't have it start like because the voice is continuous. I can't do this beamforming, so I can't talk.
No, that's not correct. It's about like how directional it is. So
because I imagine the clients will get this that don't have a direction despite the instrument playing it one place.
It does have a direction. It is coming from a point in space. And even though there is like the reflections and standing waves like that is a manifestation of the room geometry based on its location. And so that's like exactly what the this A term is trying to do that transform. So we're saying that like maybe if somebody is just holding a note on a violin, that's our like S, and it exists somewhere. And then we know that like the path from within the room to each microphone is going to, like, the different microphones are going to be different, like the walls are going to reflect it, and it's going to have all these effects. And that is modeled in the A term. And so that is like why it is a point source, is because we can say that the audio is emanating from a point. And as long as we know where that point is, where the microphones are, what all the walls are, you could theoretically like compute that transform. Yeah, I mean, that's true, but yeah, so like the air conditioner is maybe not the best example because it is kind of coming from a place. It just due to like yeah, so one example I really like is car noise. So if you're like inside a car, there's like this really loud, rumbling and whatever, and it's like, where is that coming from? It's kind of coming from all around you, and yeah, that's kind of the idea there. Any other quick questions? Okay. So the next part of this talk will be about diarization, and in particular, we're going to focus on speaker diarization. So what is speaker diarization? And it is kind of summed up in the catchphrase, who spoke when? Uh, yeah. So basically, if you have a recording with multiple people talking, and you want to know like where the speech is, and also who spoke it. And I'll add a like caveat to that we don't necessarily care about the identities of the speakers in particular, but rather we want to just track and say, a given person spoke, from this time to this time, this time to this time, this time to this time. So that's why I have these like colored regions in this recording. Like we both have identified like where speech is, and then we're kind of partitioning it into kind of like the two turns in this conversation, say. And I'll also add a quick note that there are other types of diarization. Kind of the most notable one is language diarization. So again, like diarization is mostly this task of kind of segmenting and classifying into these categories in a like label agnostic way. And we're going to talk about speaker diarization, but there are other cases as well. So the first question again is, why do we care about diarization? And one thing is that many speech systems, I use the term malfunction in multi-talker scenarios. So like, for example, if we have, a TV show or a meeting or something that we're trying to have closed captioning or transcribe. If you were to simply run a ASR system on it and get all the words out, that's not going to be remotely useful because it's just a jumble of words in the order they came in, and you don't know who said what or where sentences are or anything like that. So that can be an issue. And then also, for example, we may care about only one particular person's speech. And so you need to figure out where that person's speech is if you want to, find it. Then another note is that, again, everything isn't just about downstream applications. Sometimes you actually care about understanding the conversational dynamics. So like, for example, you can, in some sense, identify something about somebody's emotional state based on how they're participating in a conversation. If they are speaking a lot in the recording versus speaking a little, they may either be in a good mood or a bad mood. Another interesting application is kind of the study of child language acquisition. So something people are interested in is how children learn to talk, and being able to put a microphone on them and identify how much speech they're being exposed to on a day-to-day basis is a valuable source of information. And then another one is social role, for example. And this was an example that came up a lot a few years back, where people love to play clips of the debates between Donald Trump and Hillary Clinton, where you can learn a lot about how those debates went by simply marking where people are talking, because there's a tremendous amount of interruptions in those debates. Donald Trump was constantly, butting in and speaking over Hillary Clinton. And so that was like a great example of like simply knowing who is speaking when tells you a lot about the recording. So brief and easy mathematical formulation. Diarization is generally considered a label-free time series multi-label classification problem. So what that means is we have some input sequence, and for each time step, we want to basically have, we want to annotate like which speakers are active. And it doesn't matter what order they're in, it doesn't matter who they are, we just need to make sure that those labels are consistent across all time. So for example, you'll have maybe a sequence of like speech frames, and your output is just going to be like a vector of a vector of length 4, with each component simply being a 1 or a 0, depending on if a particular speaker is active at that time. Then how do we evaluate diarization systems? There's two main metrics. The first is diarization error rate. And so this is essentially a sum of all of the errors that have been made. So this can be false alarms, i.e. we hypothesize that someone is speaking when no one is speaking. It can be misspeech, where somebody was speaking, but we didn't detect it at all. And then there's also speaker errors, where we did detect that somebody is speaking, but we gave them the wrong label. And so diarization error rate is simply a sum of all of the errors, and then it's normalized according to the amount of speech. And this does like double count overlapping speech. That's an important thing to note. So you can't simply look at like all of the time where somebody was speaking. It's actually the amount of speech that was present in that recording. And then the other error rate is Jacquard error rate. And this is essentially, you break it down on a per speaker basis and then just have the false alarms and misses of that particular speaker. And then it's normalized by the like total speech of that speaker. Yeah.
Voice activity detection. Like formulated parts that
Voice activity detection is part of the problem. Like that is what the false alarm and misspeech is measuring. Well, I mean, yeah. And then just a quick note about the like kind of two differences between these metrics. One big downside of diarization error rate is that since it's normalized by the total amount of speech, if somebody speaks very, very briefly and you miss them altogether, it contributes a tiny amount to the overall error rate because that person accounted for a small amount of the speech. And in contrast, Jacquard error rate, which is averaged over speakers, you're essentially asking how well you did on each speaker in that recording. So it kind of addresses that problem. However, one big issue with Jacquard error rate is that there's no penalty for like hypothesizing additional speakers. So if you have like 4 speakers in the ground truth and you have a 5th one that you say speaks a lot, it actually does not impact the metric at all. So like it's even possible to game the Jacquard error rate. If you have like discrete frames, you can compute all possible segmentations of speech, which is this tremendous, tremendous size, but you could theoretically do it. And since you're not penalized for all the extra ones that you get, you'll get all of them and you'll get perfect error rate, even though you've never actually done any diarization at all. So then in terms of how people approach diarization, there's 2 big approaches. So one is kind of a traditional clustering-based approach, and the other is a neural kind of end-to-end based approach. And I will say that as of right now, they're quite comparable in performance. I think diarization is somewhat unique in that you can do either of these and it's reasonable. Just a kind of overview of some of the upsides and downsides. So the traditional clustering approaches have kind of multiple stages in them, and these can actually be neural as well. I'm not saying that it's like purely, signal processing and statistical modeling or anything like that. It just is about having multiple components, and these are all individually tuned. But I will comment that the clustering is less conducive to doing overlap detection because you can't really cluster with overlap. Like that's not an inherent part of clustering. You have to have discrete clusters. And you can have like modified clustering algorithms that detect overlap, but they don't work as well. And there's kind of a lot of complications with that. And then in contrast, the neural end-to-end approaches, these are kind of, again, trained to just produce the outputs directly. And being able to like jointly optimize all of the entire network as opposed to having individual components can lead to performance gains. But the downside here is that they're resource intensive. So part of this is that you need to have actual training data for the diarization task, which can be kind of hard to come by. And then also there's issues of actual like runtime issues, like memory constraints, both in training and evaluation. So first I'll talk about the kind of traditional approach. There's 4 main steps to this. So the first is to do some sort of initial segmentation. So this is generally, we're talking about doing voice activity detection. The next step is going to involve some kind of speaker representation where we're kind of extracting. So in this kind of case, we've extracted a speaker representation over a sliding window. Next, there's some kind of scoring or / clustering step where we have these representations and we're trying to cluster them into, our kind of speaker categories. And then finally, there's usually a resegmentation step where we want to adjust the boundaries because our initial like sliding window is not going to necessarily produce the best boundaries of the system. And you can also correct clustering errors in this step as well. So in terms of how people do the initial segmentation, in general, this again is just speech activity detection, and people generally just use a standard kind of neural network to do this, though people have done statistical models in the past. And then there's some kind of other approaches that have fallen out of favor. One thing is to do speaker change detection. So you're actually trying to kind of segment actual speakers at this point in time. And then overlap detection is also something people try to do at this step as well. And that's harder than you would think, but it's an important problem to solve, so people try it. So next, in terms of the speaker representation, these are basically just always going to be whatever is state of the art in speaker ID. So, people have done I vectors, X vectors, D vectors, and it's usually done where they're extracted on a sliding window basis. Though again, if you're doing something like change point detection where you're trying to detect speaker changes, you can then extract on those windows directly. And then of course, people do tune the systems from speaker ID for the diarization task as well. So you can maybe try to train a speaker verification system that's better on shorter segments because we're doing this sliding window thing as opposed to longer windows. And then you can also modify the scoring backend to kind of focus on particular recordings where we don't care about all potential people, but rather only the ones that are present in that recording. So next step for clustering, clustering is clustering. Basically, you can try anything that works and it'll work, some way or another. Agglomerative clustering and spectral clustering are the two that are most common. But one comment I'll say about this is that one of the challenges is speaker counting. So for example, one thing people do is assume that they know how many people are in the recording ahead of time. So a lot of like data sets have a fixed number of speakers in them. And when people are, developing systems and publishing numbers, they're actually assuming that you know that number. And an interesting note is that clustering to the ground truth number of speakers is not necessarily optimal. So that is something to keep in mind. Then another thing you can do is you can estimate the number of speakers in a recording using whatever method you want to choose. And then finally, sometimes we don't even actually estimate the number of speakers directly, and we simply calibrate the system to have good like speaker ID performance where you can actually kind of threshold the distance metrics and do clustering from there without ever directly detecting how many clusters there will be. Then finally, a comment on resegmentation. One of the like standard resegmentation methods is this variational Bayes HMM of X vectors. And so this is a like probabilistic model where you're basically trying to readjust the boundaries based on your X vectors that you've extracted, done via a hidden Markov model. And then I'll